we can look at a mine problem just for fun. So we determine the mine problem is this: determine the optimal production schedule for extracting ore from a mine for periods T 0, 1 to 9 for a mine that is to be shut down and abandoned in the 10th period. We assume the output price is equal to 1 and that the extraction costs are a function of output extraction, and we take the square of output extraction divided by xt. So as xt falls, the cost goes up, and as you increase the amount of ore you remove in any period of time, any year, then the cost goes up as well in a quadratic. We assume no discounting just for convenience, and we define net revenue. Let me see if I can find my cursor here. Net revenue, or profit rather, as price times the amount of ore extracted in the period minus the cost, y squared over x squared, and we can, because price is 1, we can rewrite this as follows. And what's key here is this little thing there, because it makes everything tractable without having to go to some kind of a mathematical programming package such as GAMS. And of course we have, this is our equivalent of the growth function that we saw previously, and what we find here is that the change in the amount of ore that's in the mine is equal to minus y, the extraction in any given period, and we assume that we start with 1,000 units of ore. So how do we solve this? Well, we form our Lagrangian for the mine problem as usual, and again a key figure here, or key value here, is the choice that we make with regards to that little y over x t. So here's our Lagrangian. This is the objective function again, and then again these constraints, which are, we got a t plus 1 here, and because of that t plus 1 there. So the first order conditions are, again, this number 1 is our maximum principle, where we take the partial of the Lagrangian with respect to the control variable, how much ore we remove from the mine in any given period of time, and we find that equation and set it equal to 0. We do the same thing with the amount of ore left in the mine at any given period, and we set that equal to 0, and finally we take the partial of the Lagrangian with respect to lambda t plus 1, and we end up with this third equation here, which we hold. Now notice that these equations hold for different time periods. This one holds for periods 0 to 9, this one from 1 to 9, and this one from 0 to 9. So this gives us 10, this gives us 10, and this gives us 9 as well. So with x0 equal to 1,000 and lambda 10, we set equal to 0. So in other words, recalling our discussion above, we take all the ore out until that lambda is 0. So in other words, we're saying that we can't take all of the ore out, and we'll see that in a minute. So the first order conditions represent a system of 31 equations and 31 unknowns. T is for t 0, 1 to 9, that's 10. Xt is for 0, 1 to 10, and I think I got that wrong up here. The xt should be, this should be a 10. And then we have the other one is for lambda t, that goes from 1 to 10 as well. So we end up with 31 equations and 31 unknowns. Now the key, as I mentioned before, was this possibility here, setting zt equal to yt over xt. So we rewrite equation 1 with the zt, so we get zt equals 1/2 1 minus lambda t plus 1. Since lambda 10 is 0, we can find z9 being 1/2 using this equation, and then rewrite equation 2 as lambda t zt squared plus lambda t plus 1. So if we're given that lambda 10 is 0, we can find z9 to be 0.5 from equation 1a rather. Then lambda 9 is given by equation 2a, where z9 is squared, so 0.5 squared is 0.25, and lambda t plus 1 for 10 here is 0. Then we can find z8 from equation 1a again, lambda 8 from equation 2a, and so on down. So we basically end up with determining this column first, followed by this column. Then we reverse this column. We reverse these numbers in the first three columns, so that instead of going from 0 here up to 10, okay, it's going to go from 0 down to 10. So in other words, these two values here are simply given by these two values here, and so on as we move up in these two columns along here. And from that we can use the result that y over x is z, and from that we can decompose z into y and an x. And the important thing to realize here is that as we go down in the 10th period, there's no harvest. It doesn't pay to harvest, which is why the lambda is 0. And we notice that 50 units of the 1,000 that we started with are still left in the mine. So that is our complementary slackness condition there. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.